Coefficients are the coefficients in the expanded version of a binomial, such as x plus y raised to the fifth power. Now, what happens when we multiply such a binomial out? Well, let's actually expand x plus y to the n for various values of n. Each of these are done by multiplying everything out, which you might refer to as foiling, and then collecting like terms. Let's start with x plus 1, or x plus y raised to the 1 power. Well, this is just x plus y. You don't really need any foiling there. Let's do x plus y squared. Well, this is x plus y times x plus y, which if you FOIL everything, we have x times x times y times x, and y times y. This is x squared plus xy plus yx plus y squared, which you can combine those two terms to make x squared plus 2xy plus y squared. All right, now let's do x plus y to the third power. This one, we're going to need some room, so I'm going to erase everything here. If you still needed that, you can back up a few seconds and write those down. All right, let's do x plus y cubed, which is, hold on, I'm trying to get this to work for me. There we go. Okay. X plus y times x plus y times x plus y. Now, how do we FOIL in this scenario? Well, unfortunately, when you're in high school algebra, you're taught how to FOIL two binomials. But in this case, we have three. So how do you do that? Well, you have to find every way of combining these x plus y. So we can do x times x times x. We could do x times y. We could do x times x, and so on. So there are a lot of different ways of doing this. However, let's start one at a time. So we can do x times x, which is x cubed. So that was the first one here, the first one here, and the first one here. The next one we can do x times y, which is x squared y. We can do x times y times x, which is x squared y as well, xyx, which is x squared y. We can do x times y, which is xy squared. We can do y times x, which is x squared y. We can do y times y, which is xy squared. We could do y times x, which is also xy squared. And then we can do y times y, which is y cubed. Now, if I did this right, and we can combine like terms to get x cubed plus, let's see how many x squared y's we have. 1, 2, 3 of them. 3x squared y plus 3xy squared plus y cubed. Wow, that's a lot. It's a lot of foiling. So again, we did literally every combination, but we picked three terms. One from here, and one from here. And so we would either pick like an x here, and a y here, and that would be that term right there. Or we could do a y, x, y, and you do every single combination to get all of these, let's see, 1, 2, 3, 4, 5, 6, 7, 8 different combinations, 2 to the third power, 8 combinations. And so that's the expanded version of x plus y all cubed. Well, x plus y to the fourth. This one is a little bit more daunting, of course, but we have to do it. We definitely should. Let's see here. X plus y to the fourth power is x plus y times x plus y times x plus y times x plus y. So we could do x, 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 y, x, x, y, x, 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 y, y, x, y, x, 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 y, y, x, x, y, x, y, x, y, 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 x, 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 y, x, x, y, y, x, y, x, y, x, y, 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 x, x, y, y, x, y, 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 x, and y, 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 y. That's 16 different ways of pulling either an x or a y from each of these binomials here. Now, I'm not going to sit here and write all of those 16 terms out. I recommend you do that. And I'm just going to kind of simplify this. So for my x to the fourth power, I can only get that if I multiply out all the x's here. So there's only one of those. And then there's a term for x cubed y. I don't know what that number is yet. We'll get to that in a second. There's a number for x squared y squared. Plus there's a number for x y cubed. And then at the very end here, we have y to the fourth. There's only one way of getting 4 y's, and that's if you choose all of them to be y's. Now, how many x cubes y's do we have? Well, that's the same thing as choosing 3 x's and only 1 y. There's only 4 ways of doing that. Similarly, for the xy cubed, there's only 4 ways of choosing 1 x here and all the others y's. And for the last one's a little bit trickier. It would be 6. There are 6 ways of choosing 2 x's and 2 y's. Now, again, I recommend you actually expanding this whole thing out, working out all 16 different combinations, and then combining like terms. So in fact, there is a quicker way to expand these binomials. For example, consider the next one, which is x plus y to the 5th power. Now, do you want to sit there and do x plus y to the 5th power by hand? That's 32 different combinations. I don't think you're going to want to sit there and multiply out 32 different combinations. You're bound to make an error at that point because there's just so many. So let's look at x plus y to the 5th power. What we are really doing is multiplying out, again, x plus y times x plus y times x plus y. Now I'm going to write it out here so that you can have this visual again. This visual is actually really important, and you'll see why in a second. Now, if that looks daunting, go back to the case of x plus y cubed. Why do we only have 1x cubed and y cubed, but 3x squared y's and xy squared terms? So again, I'll remind you, x plus y cubed we said was x cubed plus 3x squared y plus 3x y squared plus y cubed. So again, the question is, why do we only have 1x cubed and 1y cubed terms, but 3 x squared y terms and 3 xy squared terms? Well, every time we distribute over an x plus y, we create two copies of what is left. One multiplied by x, the other multiplied by y. So to get x cubed, for example, we need to pick the multiplied by x side every time, since we don't have any y's in the term. This will only happen once when you have those three binomials, those three x plus y's. There's only one way you can pick an x from each of those terms. On the other hand, to get x squared y, we need to select the x side twice and the y side once. In other words, we need to pick one of the three x plus y terms to contribute their y. Similarly, in the expansion of x plus y to the fifth here, there will only be one x to the fifth and one y to the fifth term. This is because, let me real quick write that out here. We're going to need a lot of room for this one. So again, there's only, this has to load real quick. There we go. There's only one x to the fifth. That's because each time we go to one of these binomials, we're either picking on the x side or the y side. And so why is there only one x to the fifth? Well, there's only one way to pick 5 x's here. You have to pick x every single time. And for the same reason, we're also going to have a y to the fifth at the end here. For the same reason, you're going to have to pick a y each of those 5 times. So to get terms like this, we need to get terms like x, let's do x to the fourth y. We need to use 4 x's and 1 y. So we need exactly one of these 5 binomials here, exactly one of them, to contribute a y. Well, there are 5 choices for this. The y could be picked from the first binomial or the third one or the fourth one or the second one or the fifth one. So there are 5 ways to get x to the fourth y, meaning that this coefficient should be 5. This is also the coefficient, by the way, for x y to the fourth. For the same but flipped reason, there are 5 ways to pick which of the 5 binomials contribute the single x in that scenario. So far, we have this. We still need the coefficients of x cubed y squared and x squared y cubed. In both cases, we need to pick exactly 3 of the 5 binomials to contribute one variable. So here we have plus something x cubed y squared plus something x squared y cubed. We're still trying to figure out those 2 coefficients. Wait, this sounds familiar. We have 5 things. Each can be one of 2 things. So we have 5 things here. 1, 2, 3, 4, 5. Each can be one of 2 options. And we need a total of 3 of them in both of these scenarios. That's just like taking 5 bits and making sure exactly 3 of them are 1s. So the coefficient of x cubed y squared and also x squared y cubed will be exactly the same as the number of bit strings of length 5 and weight 3, which we found earlier to be 10. That was in a previous video. So we have x plus y to the 5th power equals x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus y to the 5th. These numbers we keep seeing over and over again. That 10 we've seen at least 3 or 4 times now. They are the number of subsets of a particular size, the number of bit strings of a particular weight, the number of lattice paths, and the coefficients of these binomial products. We will call them binomial coefficients. We actually even have a special symbol for them. These numbers are considered n choose k. In the next video, we will gather together notation and interpretations of the binomial coefficients. I'll see you then.